In this and the next video, we will see another examples of conjugate priors. But before we continue, we need to learn some new distributions. And the one we will learn now is called a gamma distribution. Its probability density function is given as follows. It is parameterized by two parameters, a and b. Those are assumed to be positive. Gamma is also assumed to be positive. That is, the gamma distribution is a distribution over positive axis. Its probability density function plots look as follows. So you can see it can be either a unimodal distribution or it can be a exponential decaying one, depending on which parameters we will choose. Its functional form is gamma to the power of a minus 1 times the exponent of minus bx, b gamma. For some parameters, the first term is increasing function, the second term is decreasing function, and so we can model the unimodal distribution. The normalization constant looks as b to the power of a over gamma function of a. The gamma function is a smooth extension of a factorial. That is, the gamma at point n equals to the n minus 1 factorial. For example, gamma of 5 equals to 24. Its statistics are given as follows. The mean value equals to a over b, the mode is a minus 1 over b, and the variance is a over b squared. Let's see example how we can apply the gamma distribution to model real things. Imagine that you run every day. You run somewhere around 5 kilometers. However, some days you're a bit more active, some days you're a bit tired. And so you can run 100 meters more or 100 meters less. This means that the expected value of the distance that you run is 5 kilometers and the variance is 0.1 kilometers squared. So we can model this as a random variable that has a gamma distribution. We could also use a normal distribution. However, it would imply that you can run a negative distance, which is impossible. So we can plug in those values into the formulas for the mean and the variance and find out that a should be equal to 2500 and b should be equal to 500. And the probability density would look like this. The gamma distribution is actually conjugate to the normal with respect to the precision. I haven't defined precision yet, so let's do it now. The precision is inverse of the variance. For example, here the blue curve has high precision, that is, you can easily predict where the samples would be. However, it has low variance, and the green line would have high variance and low precision. So here's the probability density function of a normal distribution. If we replace the variance with the inverse of the precision, we will get the following formula. Now we ask ourselves what is the conjugate prior with respect to the precision. So here's our formula again. If we drop all the constants that do not depend on gamma, we'll get the following function. Let's try to find the conjugate distribution in the following way. It would be proportional to gamma power 1/2 times the exponent of minus b gamma. Will it work or not? What do you expect? Alright, let's check it out. Here's our base formula. Again, we can drop the denominator since it does not depend on the parameters, and we'll get the following functional form. If we rearrange the terms, we see that the gamma now has the power of 1, which means that it doesn't lie in the same family of distributions. The one that we considered before had the power of 1/2. So this is a wrong answer. What if we choose a gamma distribution? That is, we'll have another parameter that would allow us to vary the power of the gamma. That would look like follows. So again, this is gamma distribution parameterized by two parameters, a and b. Well, let's try to compute the posterior. Again, here is our prior. Here's our posterior. It is proportional to the likelihood times the prior. Here's what we get if we drop all the constants. And if we rearrange the terms, we'll get the gamma to some new power times the exponent of the minus gamma times new constant. And so we can estimate the parameters of the posterior from this form. So the mean would be a plus 1/2, and the variance would be b plus some quadratic term. And so we avoided computing the evidence simply by choosing the conjugate prior.